Number 23 says the net ionic equation for the acid-base reaction of chlorous acid with potassium hydroxide is. Might want to just try writing it out yourself. So it would look like HClO2 plus potassium hydroxide, which is KOH, and you get, and think about like what could possibly form. So the H is going to pair up with the OH to form some amount of water. So we can actually just put that here, H2O. You can think of water as HOH. So think of it as like HOH. That's your H2O. And what's left over? You get potassium chlorate, or potassium chlorite. That's ClO. So ClO2 minus is the chlorite ion. So that's your overall equation. To get your net ionic equation, you need to break it apart to see what's going to be, what the spectator ions are and what's going to cancel or not. You have to recognize that HClO2 is a weak electrolyte, so this is not going to associate very much, so you're going to keep it together. HClO2. However, potassium hydroxide is a strong base. It's going to be a strong electrolyte, so it's going to be broken apart into the K plus and the OH minus. On the other side, water is just water, and potassium chlorate is going to be floating around in solution as well. It's going to be K plus. I'm going to move this for space. It's going to be K plus. So the potassium ion plus the chlorite ion. And what is going to be the net equation? Cross out things that appear the same on both sides. So let's first review again why I did it this way. This is a weak electrolyte. It's basically not going to dissociate much. But the potassium and the hydroxide, the potassium and the hydroxide coming from the potassium hydroxide are going to split apart. They're going to be floating apart in that solution. You're going to get water formed from a little bit of the H coming off to mix up with the OH. So there's a little bit of that going on. But the spectator ion overall is still going to be the potassium. I'm going to cross out the potassium on both sides. And then what you get is you get HClO2 plus, you have your hydroxide. It's going to form water and the chloride ion. And that's going to be your net ionic equation. So let's check to see if those make sense. So we have completely together here and here. So that's out, out, out. So that's completely together. And then the hydroxide is really a key part. So we want that to be separated as well. And here it's not, so that one's out. So this is your answer. Notice how the charge is conserved as well. So nothing plus 1, or nothing plus -1 is -1. You have a nothing plus another -1 is -1. So your total charge on both sides is conserved, and that's a really important thing to know as well. Number 23, what is the temperature of 2.80 grams of nitrogen if its volume is 1.85 liters and its temperature is 1.35 atmospheres? Simple ideal gas law equation where you have to make sure things are right. Now, in this case, you're solving for temperature. So to do that, you're going to take your equation, move it around using algebra, and you're going to get that the pressure times the volume divided by N times R is going to equal the temperature. Remember, temperature must be in Kelvin mathematically. Notice how all your answer choices are in Celsius. That's because you're going to turn it into Celsius. So the pressure is 1.35 atmospheres. The volume is 1.85 liters. Number of moles is, we have a small problem, but that's an easy one to fix. 2.80 grams of nitrogen. Turn that into moles of nitrogen. So put grams on the bottom and moles on the top. Grams cancel, top and bottom. And then the molar mass of a single nitrogen is 14. Double that and you get 28. And turns out that 2.8 divided by 28, I don't know why I'm using a calculator because it really is obviously just 0.10 moles. and then the R is 0.0821 for atmospheres. Doing all that math there, you get 1.35 times 1.85 divided by the product of 0.1 times 0.0821. I got 304.2-ish degrees Celsius. Or degrees, sorry, I almost was trying to think ahead. 304.2 Kelvin. And notice how that answer option is here. It seems, but that's in Celsius. Don't forget that you need to convert that into Celsius by subtracting 273. And to do that, just subtract 273 and you get about 31.2 degrees Celsius. So it's this one right here. Remember, when your math is done using the ideal gas law equation, your answer is going to be in Kelvin, but you need to convert to Celsius perhaps. This question's asking you to do that. If this question didn't have C's and it instead had a bunch of K's, then your answer choice would be this one, but it's not. It actually asks for Kelvin, or it asks for Celsius, so make sure you convert your Kelvin into Celsius. For number 25, it says you have exposed electrodes of a light bulb, like this, in a solution of sulfuric acid, which is a strong acid, so it's a strong electrolyte, such that the light bulb is on. We know that current will pass through a solution of electrolytes. If you add something and the light bulb gets dimmer, so like the light bulb loses some of its shine, what would possibly be the solution that you added? You can think of it this way. You're adding something that is going to cause the overall number of ions or electrolytes to decrease. So looking at the answer choices, we have an ionic solution, an ionic solution, an ionic solution, and we have a basic solution where we have ions in the solution. This is actually a strong base. So let's think about what would happen where we have a strong acid, we have H2SO4, and we were to add an ionic solution to it, such as calcium nitrate. Then you'll just get, for the most part, you won't have a reaction in the sense of an acid-base reaction. You'll just get a lot of extra ions. You're introducing more ions in the solution, and nothing really will happen other than it might even get brighter. So you're looking for something where you're reducing the number of ions in the solution overall. This is just adding more ions. You're adding calcium and nitrate ions. Calcium nitrate is pretty soluble, and for that reason, it's going to just stay as a bunch of calcium and nitrate ions in addition to the hydrogen and the bisulfate ions you already have, and it's just not going to reduce the number of ions in the solution. So the first one's not a good option because you're just adding ions instead of really removing any. The same is going to apply for sodium nitrate because sodium is very soluble when it comes to hooking up with nitrate. So sodium nitrate is very soluble, same thing. K2SO4 is a salt that is also soluble, but here's why barium hydroxide would be a better option. If you add barium hydroxide to the solution, what you're going to get to some extent is, based on your solubility rules, you're going to, or not solubility rules, but based on the acid-base reaction and a little bit of solubility rules, you're going to actually form some water because think about the fact that hydrogens from the sulfuric acid are going to hook up with the hydroxides, and the hydrogen ions that are floating around are going to be attracted to the hydroxide ions that are floating around. So let's think about what's happening in the solution. You have H pluses floating around, so let's do a couple of H pluses, along with, of course, the bisulfate, which is the SO4 minus. But you have H pluses floating around. If you introduce some hydroxide ions, so you add some OH minuses, you're going to add some amount of OH minuses, right? What's going to happen is that these are going to link up to form water. So you're actually going to have a net reduction in the number of ions that are present in this solution. And that's because you're taking some of the hydrogen ions, which help with the conductivity, and you're adding in some hydroxide ions, but those are going to link up with the existing hydrogen ions and you're going to actually end up getting water. So what that's going to look like is this. There's going to be some amount of neutralization, and that's why your light bulb is actually going to get dimmer if you add some barium hydroxide, because you have an acid and you're adding a base, and you're going to cause some neutralization, in which case you create water rather than more ions. So that's why that's your answer for number 25. 26 is just a honor code. 27. What is the molarity of an aqueous solution of nitric acid if 26.85 milliliters of that solution is required for the complete titration of 25 milliliters of 25 milliliters of this molarity of barium hydroxide? So for this question, you are going to have to do aqueous chemistry calculations, which is like basically kind of like a dilution. So moles of acid times the volume of acid is going to be equal to the moles of the base times the volume of the base, the molarity of the base, I should say. And what you have over here is moles of acid and moles of base. The reason for this is that molarity is equal to moles over liters, but we could just say V for liters in this case. You don't have to convert to liters because they'll cancel out. You're using milliliters and milliliters, so we can just put a V here. And of course, if you multiply both sides by V, you get that M times V equals moles. And at neutralization, which will happen during titration, you will have moles equals moles. Moles of acid equals moles of base. So let's actually use the numbers we have to figure out what's going on here. Concerning the acid I'll do in red, we want to know what is the molarity of a certain volume of acid. So we don't know the molarity of the acid. We know the volume of the acid. We do not have to convert to liters because they'll cancel out, but you can if you want. I'm just going to keep it as milliliters. 26.85 milliliters is going to be equal to, do we know the molarity of the base? We do. Do that in blue. So the base, the barium hydroxide. The molarity is going to be 0.255, and then the volume is 25. There's a small problem though. What actually matters is not the nitrate and the barium, it's really the hydrogen ion and the relative number of hydroxide ions. So it might help you to figure out your the concentration of the hydroxide ions, which would literally be twice this number. So let's think about this. If you have 0.025 molar of the barium hydroxide ions, I'm going to sketch this out in green. So you have 0.255 molar barium hydroxide over 1. Remember that molarity is really just moles over liters. So I'm going to back this up into this. You have 0.255 moles of the barium hydroxide for every 1 liter. But let's consider that when it comes to titration, what matters is the hydrogen ions and the hydroxide ions. So we're going to go from moles of the barium hydroxide to moles of the hydroxide ion, because that's actually what makes something a base in this case. And for every 1 mole of barium, you have 2 moles of hydroxide. So we're going to actually find the molarity. Notice how we're going to deal with the molarity of the hydroxide ion, which is literally going to just be double that. So 0.255 times 2 is 0.51. So we have 0.51 molar as our concentration of the hydroxide ion. Nitric acid has, this nitric acid here, it just has 1 H for every 1 mole of HNO3, and it's strong, so you're going to get 1 mole of H's. What's going to happen here is HNO3 becomes a mole of H's and a mole of nitrates. But thinking about what happens for the dissociation of barium hydroxide, a barium hydroxide becomes a barium, which is 2 plus, and 2 moles of hydroxide, which we actually are expressing here because we set it right there. All that to say, you need to use this number in your titration. It's going to take twice as much nitrate to neutralize every 1 mole of barium hydroxide, because think about the fact that every mole of barium hydroxide has twice the number of hydroxides. So we're going to replace this number here with our 0.51 and get rid of all this extra work stuff. And then you can solve your neutralization equation. So we're going to divide both sides by this, and we're going to have our answer, which is going to be what is the molarity of an aqueous solution of this strong acid that would neutralize this strong base. Turns out that this strong base kind of acts as a double base. Like every mole of barium hydroxide gives you twice the number of hydroxide ions. So let's figure out what our math is going to be. Multiply that by 25 and divide that by 26.85. And we get 0.475, and that's going to be our answer. It's really easy to use the wrong molarity for the base if you forget that this particular base has twice as many hydroxides. So it's got to be neutralized twice, so to speak. If you use the wrong numerator here, you would have an answer that is half of this. And it makes sense that one of the distractors is this incorrect answer there. Number 28. What is the volume of 0.05 or 0.550 molar iron 3 nitrate solution needed to supply 0.950 moles of nitrate ions? So really, again, remember, molarity is equal to moles over liters. Now we're looking for volume, so we need to rearrange this to solve for L. So liters is equal to moles over the molarity. Keep in mind your units are not what they should be right now. We can fix that later. So we know we need 0.950 moles of nitrate. And we have the molarity of the iron 3 nitrate solution here given. But remember, just like we've seen with the last example, if you have iron 3 nitrate, which is going to be a strong electrolyte, so it's going to completely dissociate, it's going to dissociate into 1 mole of iron 3 for every 3 moles of nitrate, based on the coefficients, the 1 mole for every 3 moles of nitrate. So with this information, we can actually do a conversion with the stuff that we have from here. So you actually work it backwards, 0.950 moles of NO3 minus. Let's convert that from moles of nitrate to moles of the iron 3 nitrate that it comes from. And when we do that, we're going to have a big 1 in front of the iron 3 nitrate, and it makes sense that it gives us 3 moles of nitrate. It's really easy to go the wrong direction, so make sure you're careful with it. Dimensional analysis will help us here. 0.950 moles of nitrate. How many moles of iron 3 nitrate would that be? Let's do our division. 0.950 divided by 3. We're going to get 0.316 repeating moles of the iron 3 nitrate. So this is how many, so far we have this number of moles of iron 3 nitrate is what you need to require this many moles of nitrate ions. And it makes sense because for every 1 mole of iron 3 nitrate, you get 3 times as many nitrate ions, so you only need 1/3 of the iron 3 nitrate to give you this many nitrate ions. So dimensional analysis can actually help us carry us all the way through the end. So we have this many moles of iron 3 nitrate, which is equivalent to this many moles of nitrate ions when it dissolves. Let's convert our moles of iron 3 nitrate into liters of iron 3 nitrate. Now remember, molarity is a conversion factor between moles and liters. So we know that for every 1 mole of iron 3 nitrate, or for every 1 liter of iron 3 nitrate, we'll have 0.550. So right here, this is just the molarity equation upside down. So we have that here. using this conversion factor. So moles of iron 3 nitrate are gone. We currently have liters of iron 3 nitrate necessary, but we can actually take it one more step, going from liters of FeNO3, because notice how all your answer choices are asking you for milliliters. So that's what we're going to do here. We're just converting liters to milliliters using a simple conversion here. Every 1 liter has 1,000 milliliters. And when you do your numbering and your math, you get 576 milliliters of FeNO3. So a review of what just happened. We didn't really need this part actually. It's actually probably easier to do it doing dimensional analysis. So what we have is we figured out that the equation is going to say for every 1 mole of iron 3 nitrate, we'll get 1 mole of iron, 3 moles of nitrate. And the math we did showed us that we just need a third of it. So we turned our moles of iron 3 nitrate into liters and then liters into milliliters, and that's going to be your answer. Number 29, a gas occupies a volume of 3.78 liters at a certain temperature and pressure, with the volume at a new temperature and pressure. Pretty simple that this is the combined gas law, which you may see in one of two forms, but you can also solve it by setting the ideal gas law equal to or above the other ideal gas law. So this is the initial conditions. Let's see, I'll make this all style red. So initially, it was this volume, this temperature, this pressure. We are assuming, of course, that the number of moles of gas is constant as well as R. I'm just going to duplicate this, change the color to blue, because blue is going to represent the volume of the gas at the new temperature and new pressure. So we can change all these little ones into twos, because that's going to be the final condition. And then divide. Now remember, remove everything that is constant. So I'm just going to literally erase it this time. Moles of gas is constant, R is constant, and you're just left with this information. And we move the fraction bar, make a single equal sign, and what you get is this. You get that the initial conditions on top are equal to the initial conditions on bottom. And just as a further reminder, you might see the ideal or the combined gas law written out this way as well. It is all the same. Okay, so with that being said, you can use either one of these you want. They're the same thing. But as long as you realize you're solving for V2. It turns out that the second one's a little easier to work with because V2 is already in the numerator position. So I'm just going to get rid of this one. This is all just about being careful with your math. So to do this, I would divide both sides by P2. So P2 is going to go downstairs. And then T2, multiply both sides by T2 is going to go upstairs. And then this is going to be what it is. So volume, the final volume is equal to the final temperature times the initial pressure times the initial volume divided by the product of the final pressure times the initial temperature. And you just plug and chug everything in. So the temperature to start, we know that temperature has to be in Kelvin. So at this point, you're just automatically turning things into Kelvin. And the initial, or the final temperature, I should say, is 40 plus 273, 313. Initial pressure given in atmospheres. Oh, there's one other thing that's kind of tricky. The pressure here is given in atmospheres, or millimeters mercury, and then the final pressure is given in atmospheres. You can use whichever one you want. Just remember there's a conversion factor. 1 atmosphere is equal to 760 millimeters of mercury. So you can convert. Let's actually just handle that right now. It doesn't matter which one you use to turn which one into whichever. I'm going to turn... doesn't matter at all. I'm going to turn this into atmospheres. So 680 millimeters of mercury is equal to, so convert millimeters of mercury into ATM. 1 atmosphere is 760 millimeters of mercury, and then you get 680 divided by 760, 0.895 0.47, blah, blah, blah. Just keep those extra digits in your calculator. And then our volumes are both in liters, so that's good. Initially, it was 3.78 liters. Divide that carefully by your final pressure, which is 1.2 atmospheres. I decided to keep atmospheres for both, so atmospheres, and then I turned this into atmospheres. But if you wanted to turn the atmospheres into millimeters of mercury, you can go ahead and do that, as long as your units are the same for both of the pressures. And then our temperature to start, so our T1 is 30 plus 273, which is 303. So doing all this math, you get 313 times 0.8947 and some stuff times 378, or 3.78. Press enter and divide by the product of 1.2 and 303. I get about 2.91 liters of gas. So where do you avoid pitfalls? First of all, make sure your pressures are in the right same units. Doesn't matter which unit, as long as they're the same unit. This is an important conversion factor to memorize. Also, make sure your temperatures are in Kelvin, and then just set up your equation correctly. This question, number 30, is an ideal gas law stoichiometry question. You have non-standard conditions here. It says the reaction that takes place in a car's airbag to inflate it is 2 moles of sodium azide decomposes to create 2 moles of sodium and 3 moles of nitrogen gas. What mass of sodium azide is required to provide the nitrogen needed to inflate a 6-liter bag to a pressure of 1.25 atmospheres at 298 Kelvin? That's a lot to think about. And I've seen these as free response questions, which makes it even worse. But how do you do one of these problems? First of all, it asks what mass is necessary. So that means you need to first solve for moles using the ideal gas law. Then you got to do stoichiometry after it. So step 1, take your information P, V, N, R, and T, and just kind of do a problem solving strategy where you see what do you have. We know the pressure needed is 1.25 atmospheres. The volume is going to be 60 liters. We don't know anything about the number of moles of gas. If we're sticking with atmospheres, that means we're going to use 0.0821 atmosphere liters per mole Kelvin. And temperature is going to be 298. So it's already in Kelvin. That's great. Now notice how if you set up your ideal gas law equation and you don't have N, that's really easy to do. So all of this, it's all for N. N is going to be equal to PV divided by RT, so pressure, 1.25. V, 60. R is given as 0.0, well, not given, but it's probably going to be in your constants, 0.0821, and then T, 298. So all of that together gives you how many moles of gas there are. And then you've got to do stoichiometry, because keep in mind, this is the gas that we're talking about. All of this stuff, this relates to the nitrogen gas. You're asked what mass of Na3 you need. That's this stuff here. So that's something important to really note too. These are trickier problems. So 1.25 times 60 divided by 0.0821 times 298. And you get about color coding, 3.066 approximately moles of nitrogen gas. This number here is important, but it's not your answer. That's going to lead us to step 2. Step 2, you need to take that number of moles of gas, 3.066 moles of N2, and you need to convert it. So we're going to go from moles of N2 to moles of, and this is stoichiometry, by the way. So the second part is going to be stoic, and the first part is going to be the ideal gas law. So remember, for stoichiometry, you look at the ratio of the coefficients. So we're actually going to work backwards, and we're really answering the question of, well, in order to get this many moles of nitrogen under these conditions, how much of the sodium azide do you have to even start with in the first place? That's what this is asking. So it's working backwards. So we have NaN3. Looking at our balance equation, we have 2 in front of the sodium azide, and we have a 3 in front of the nitrogen. That should be a 3. Why did I write a 2? There we go. All right, so canceling out your units, moles of nitrogen are gone. And we're actually almost at that very last step, which is now convert your moles of sodium azide into grams of sodium azide, which is given here as 65 grams per 1 mole. And that's going to be your answer. So we're going to multiply that 3.0 whatever number times 2 times 65 and divide it by 3. And we get about 133 grams. And that's how you do that one. So first, I would recommend set up your ideal gas law equation and note that you do not have moles. Solve it. Once you have moles, run it through to figure out how much of the starting material you need to even get that many moles of the gas in the first place. This last question says, a lab technician needs to prepare 3.75 liters of a 0.22 molar solution of nitric acid from a solution of nitric acid that has a much higher concentration. How many milliliters of this higher concentration solution do they need? So this is simply a dilution equation problem where it says that the initial molarity times the initial volume is going to be equal to the final molarity times the final volume. And if you go through the problem carefully, you should be able to identify them. So the amount of volume needed at the end is 3.75 liters. And the molarity of the concentration, or the molarity of the solution needed at the end, is also given. Now this is going to be dilution, so the initial molarity is much higher. That's going to be M1, and you're looking for V1. So V1 is, we don't know. That's what you're figuring out. How much of this concentrated solution do they need in order to create a more dilute solution? So the dilute solution is going to be here in green, and that's going to be what you're making at the end. And then the concentrated solution is what we're trying to figure out, where it says how many milliliters are needed. Now, to be very, very careful here, notice how this is something that professors can do to trick you. You have liters needed, and it asks for a milliliter. So dilution problems are super simple. The only way to really make it hard is to mess with the units. So let's try it. Whatever units you want, get it there. I would recommend you actually take this 3.75, so 3.75 liters, and turn those into milliliters. So liters to milliliters, 1,000 milliliters is a liter, and you get 3,750 milliliters. And that's going to be, by the way, your V2. And then you just plug everything in. So the rules of math say that if you divide everything to get V2 or to get V1, you'll get, V1, initial volume, is going to be equal to M2 times V2 divided by M1. And you just plug everything in. The concentration on the red side, so to speak, so the concentrated solution is 15.8. The volume, actually, let me go back. The green side, the final volume and the final molarity are going to be 0.22 for the molarity and 3,750 for the volume. So we just took this and we made sure to get it into milliliters. That way we don't have to worry about it at the end. So we got milliliters. Divide that by the M1 and you get 15.8 down there, and you do your math. 0.22 times 15 or times 3,750. Then divide that by 15.8. That's going to give you about 52.2 5.2 milliliters. So that kind of makes sense because you need only a little bit. You only need 52.2 milliliters. That's not a lot. You only need a little bit of this very concentrated solution in order to get a lot of a much weaker solution. So that's what the dilution equation is saying.